Hello, today I'll be presenting the abstract Optimization of Combined Spin and Gradient Echo EPI and fMRI via in and through plane acceleration. We have a research agreement with Philips Healthcare. Blood oxygen level dependent or BOLD functional MRI is widely used to study both task-induced functional activation and resting state functional connectivity. Acquiring fMRI with gradient echo EPI presents several challenges, including signal dropout and image distortion near air tissue interfaces, namely the inferior frontal and temporal lobes. Additionally, while gradient echo fMRI is sensitive to the BOLD contrast, it is also dominated by large vessel effects, despite the contrast-associated metabolic exchange taking place in the microvascular capillary beds. Alternatively, spin echo fMRI is sensitive to the microvasculature and refocuses susceptibility-induced dropout seen in gradient echo acquisitions. However, spin echo is not as sensitive to the BOLD effect. To improve acquisition in high susceptibility regions and increase sensitivity to microvasculature, we propose use of a combined spin and gradient echo or SAGE acquisition in fMRI. SAGE leverages multiple echoes and contrasts, including two gradient echoes sensitive to macrovasculature, two asymmetric spin echoes sensitive to both macro and microvasculature, and a true spin echo sensitive to the microvasculature. Multi-gradient echo imaging has been shown to improve BOLD sensitivity and signal-to-noise ratio in regions with susceptibility effects, and the addition of spin echo imaging will provide sensitivity to microvascular effects. We hypothesize that SAGE fMRI will improve acquisition in high susceptibility regions and provide complementary microvasculature-sensitive information. SAGE fMRI presents its own challenges, namely inability to acquire full brain coverage and inadequate spatial and temporal resolution. To acquire full brain coverage and improve spatial and temporal resolution, we aim to identify the optimal SAGE fMRI protocol by testing combinations of multiband RF excitation and sensitivity encoding acceleration factors. By leveraging acceleration factors, we can acquire full brain coverage and improve spatial temporal resolution. However, implementation of acceleration factors can result in lower signal-to-noise ratio. Therefore, we aim to balance acceleration with image quality. We collected data in 6 healthy volunteers on a 3 Tesla scanner. Acquisition parameters are below for our SAGE sequence, and additional parameters are in the table to the right. Of note, the multiband factor 1 was not able to acquire full brain coverage, and multiband 4 fifth echoes were too long. Data underwent minimal pre-processing before being fit to obtain voxel-wise R2 star and R2. Temporal signal-to-noise ratio was calculated using the equation below, and statistics included a one-way ANOVA model to test the differences in mean group TSNR and mean group T2 star and T2 values across acceleration factor combinations. Tukey's HSD was used for post-hoc analysis. Using a multiband factor enabled us to acquire full brain coverage, so multiband 1 was unable to. Qualitative analysis of the second and fifth echo revealed loss of signal and image quality in multiband 4 across sense factors. At this point, multiband 2 and multiband 3 combinations seemed most optimal. Quantitative assessment of TSNR via pairwise comparisons revealed no significant differences in TSNR between any of the multiband 2 and multiband 3 combinations across sense factors. Notably, the sense 2 factors had fifth echoes that were longer than 100 milliseconds as well, so we ended up choosing the multiband 2 and sense 2.5 factor because it was acquiring our full brain coverage and maintaining the highest TSNR. In addition, there were no significant differences found between T2 star and T2 values across our multiband and sense factors, supporting that we can move ahead with the multiband 2 sense 2.5 combination. Lastly, we did compare our T2 star and T2 SAGE-based maps to standard maps for T2 star and T2 and found that the values were comparable. In conclusion, a combination of in-plane and through-plane acceleration factors can be leveraged to optimize SAGE fMRI. SAGE fMRI may improve spatial localization of brain activation and be useful in imaging studies concerning the medial temporal and inferior frontal lobes. Future work includes comparing task-based and resting state SAGE fMRI to single echo methods. Thank you for your attention and to the sources of funding for this work.